Okay, so some of us are on strike, so you may have seen these leaflets. I'm not because I don't support the cause of the strike, but because I think me striking is not going to help matters in any way, right? I'm just being strategic. But yeah, this is a fair cause. I think we have a fair claim, and those of you who were here in the previous lecture probably have heard all about it, more than you wanted to know. Right, anyway, so, right, yeah, so I don't bother with that because I'm thinking strategically. Me telling the university to not pay my salary today is unlikely to shift the university actions one way or other. Even me not lecturing this course today is not going to affect things. Right, and strategic thinking is something that is generally very useful, and I'm leading up to the topic of this lecture, so which is zero-sum games. Well, okay, so arguably the game that is being played now between the University and College Union and the university is hopefully not a zero-sum game. Hopefully there's a way to find kind of mutually beneficial resolution. But since I want to talk about applications of linear programming, I'm restricted to talking about zero-sum games. If you want to hear about nicer games that are not zero-sum, you have to stay on for part C, and then there's a computational game theory course. Okay, so zero-sum games. Okay, so why do I want to talk about zero-sum games? Well, frankly, first because I like to talk about game theory. This is one of the things I do. Second, because I want to give you an application of LP duality. Because if you think back to what we did in the previous lecture, so I introduced the concept of LP duality. So I told you about this amazing claim, strong LP duality, value of the primal is equal to the value of the dual. But it's an algorithms course. So what are the algorithmic implications of that? Well, we talked about max flow min cut being a manifestation of LP duality, but it doesn't really cut it as an application, right? Because we have a separate flow for max flow min cut, right? And the argument that goes for LP duality is surprisingly complicated. So what I want to do now is to show you an actual, very useful application of LP duality, and that's about existence of stable outcomes in zero-sum games. Okay, so what do I have? I have two players, row player and column player, and there's a payoff matrix. So payoff matrix, it has m rows and n columns. So think of the m rows as the available choices to the row player, n columns are the available choices to the column player. So the way the game proceeds is simultaneously the row player chooses row I, the column player chooses column J, And then there's a number in that column. There's a number in that cell, ij. And that number is the payoff that goes from the column player to the row player. So the game is called zero sum, meaning the money gets transferred from one player to another player. Right? So there's no external supply of money, and also the money doesn't get burned. So what one player wins is what the other player loses. Zero sum. Okay, so to give you an example, okay, so this is a zero sum game. It's a game that all of you, I imagine, know. Rock, paper, scissors. So the row player, the green guy, has 3 actions: rock, paper, and scissors. The column player, the orange guy, has 3 actions: rock, paper, scissors. And the payoffs to the row player are numbers in the matrix. Okay, so let's check that it matches our intuition. If the action is the same, then it's a tie, so the payoffs are 0. So let's look at the off-diagonal entries. Say row player chooses paper, column player chooses rock. Paper wraps rock. Right, so the row player wins, so they get +1, and they get this +1 from the column player. The row player wins 1, the column player loses 1. Right, and you can check that generally this matrix kind of corresponds to how we play rock, paper, scissors. Okay, now how do you play rock, paper, scissors? Do you choose the same strategy all the time? No, typically you don't, right? So what you want to do is you want to confuse your opponent, right? And the best way to confuse your opponent is to randomize. Right? So the way you play rock, paper, scissors, intuitively the best way to play rock, paper, scissors is to choose each of the 3 options with the same probability. To throw a 3-sided coin, if you will. Right? So that each option is chosen with the same chance. Because right, intuitively this is your best chance to confuse your opponent. Okay, so how does it match what I describe here? It doesn't match it very well. Right? I say row player chooses row, column player chooses column. So what we really want to have to capture how this game is played in practice is to have probability distribution. I, as the row player, should be able to choose and commit to a probability distribution. And the column player does the same. Right, and then we play this probabilistic extension of the game. Okay, so how do we define it? Well, this is what is called mixed strategy. And the mixed strategy is a probability distribution on rows for the row player and columns for the column player. So my mixed strategy as a row player is to play, say, rock 50% of the time, paper 50% of the time. Right, so 0.5, 0.50 is my mixed strategy. Okay, so the way we write these strategies is as vectors. Right, so the row player has m rows, so they need m numbers. Right, so these are probabilities, non-negative numbers that sum up to 1. Right, and they're numbers for the column player. Okay, so now what happens when they play those mixed strategies? I randomize, my opponent randomizes. Then potentially each cell of the matrix may happen. Right, and it may happen with some probability. Right, and with that probability, the probability of occurrence of that cell, I get the payoff of that cell. So for instance, the probability that I get this 0, not just 0, but this specific 0, is the probability that I play scissors and my opponent plays scissors. Right, so the way to calculate it is just to take the expected value. Right, so I go over all possible cells. So the value in cell ij is aij. Right, and I get that aij with probability piqj. Right, because we randomize independently. Right, so piqj is the probability of cell ij, this is the number in that cell, and we sum up to get expected payoff. Right, and this can be written very cleanly in matrix notation as P transpose AQ. Okay, makes sense so far? Okay, good. Right, so these are zero-sum games. Okay, so what would be a good outcome of a zero-sum game? How can we predict what is going to happen in zero-sum game? Right, and here the concept of Nash equilibrium comes in. Okay, show of hands, how many people here intuitively know what a Nash equilibrium is? Maybe not formally, but okay, some hands. Okay, good. So let's define it formally. So Nash equilibrium, okay, so intuitively equilibrium is a situation when everything is stable and sort of nothing, there's no incentive for anything to change. Right, so that's sort of physical intuition of equilibrium. Right, and that's exactly what we have here. A pair of mixed strategies is a Nash equilibrium if each strategy is what's called the best response to the other. Meaning, well, I know that my opponent plays Q, so it means that I don't want to change my strategy from my P to any other potential R. Right, so if my opponent sticks to the strategy Q, then it's at least as good for me to stick to my strategy P than consider any other option. I don't want to change. Given that my opponent sticks to the strategy Q, I don't want to change. And similarly, if my opponent knows that I stick to my next strategy P, they don't want to change. They cannot do better by choosing another strategy S. Okay, so why different signs? Right, the signs are because what we write in the matrix is the payoff of row player and the loss of the column player. Right, so Aij is the loss of the column player if cell ij is chosen. Right, so what they're saying here is if I choose another strategy, my loss will be at least as large. Right, so I don't want to choose another strategy. Okay, so this is a concept of Nash equilibrium, right? No one wants to change. I play P, you play Q, none of us wants to change, right? So this is stable. Okay, reasonable questions you can ask. Do Nash equilibria always exist? And can we compute them efficiently, that is, in polynomial time? Okay, and the answer to both of these questions turns out to be yes via LP duality. Okay, so for those of you who have had some exposure to game theory, I'm talking specifically about zero-sum games, and for zero-sum games, so these are the answers. So there are also games where the win of one player is not necessarily the other player's loss, right? So there may be cells when I win 1 and you win 2, there may be cells when I win 1 and you win -1, right? So it's not always doesn't always sum up to 0, right? And then the answer here is still yes, but the answer here is sort of no. Right, and we have our own Paul Goldberg to blame for the proof of that fact. Right, so. And kind of the whole story gets much, much more complicated. But let's stick with zero-sum games, because here we can do like a 3-slide proof by LP duality, both for existence and for efficient computation. Okay, so this is what we're going to do now. So so I talked about Nash equilibrium, so let me talk about another way of thinking about strategies and payoffs. Right, so it may seem unrelated to Nash equilibrium at first, but bear with me, and we'll see that this is actually kind of a way to compute Nash equilibrium. Okay, so suppose a row player announces that she's going to play P. Okay, so what does it mean for the column player? The column player can choose any of his columns. Right, so the row player mixes. Right, so what the column player observes is the mixture of the rows of the matrix. So for each choice of the column, there is some expected loss that he is going to incur by playing that column. So specifically, okay, so let me draw some matrix here. So my matrix is going to be A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so the row player mixes. She mixes with probabilities P1, P2, P3. Right, so the column player is thinking whether they should play the first column. Okay, what is the expected payoff when they play the first column? So they get this with probability, they lose this with probability P1, this with probability P2, this with probability P3. Right, so the expected loss is the weighted average of the numbers in the first column. Right, so they can do the same computation for the second column, for the third column. Right, so each column is associated with a number. Right, so it's a loss for the column player. Okay, so which column should the column player rationally choose? The one with the least loss. Right, so there may be several columns. Right, so the loss incurred here may be the same as the loss incurred here. Right, and the loss incurred here may be greater. Right, but he should play with he should play a column with a positive probability if and only if it's one of his best columns. Right, so if I lose 2 here, 3 here, and 2 here, I should place 0 probability on playing that column. Right, because if I was placing some positive probability there, I could shift that probability mass to a kind of lower loss column, and I will be doing better. Right, so I can still randomize. I'm not saying that I should be using, as a column player should be using one specific column. But I should be randomizing among the lowest loss columns, right, among the best columns. Okay, right, so that's the constraint here. Okay, so this is how column player is thinking. Right? If the row player plays P, I should be randomizing among the columns that minimize this quantity. Okay, so that was my mental experiment. I'm actually the row player. I'm in the business of choosing P. Right, so I ran this mental experiment. I know how the column player is going to respond to my actions. Now, how should I choose my P? Well, I know that for each P, what I'm going to win is the minimum of quantities of this form, minimum over all columns. Right, so for each P, this is what I'm going to get. So I should choose my P to maximize that amount. Okay. So my play from playing P is this, minimum over all possible columns. Right? So therefore I should choose P as to maximize this quantity. Okay, so what kind of reasoning is this? So I'm not reasoning in terms of Nash equilibrium. I'm reasoning conservatively here. So I'm saying, okay, so suppose I have to commit to my mix strategy and write it down for the column player to see. And the column player will then be free to choose the response after having seen my mix strategy. Okay, if they see my P, they will make sure that what I get is at most this, right? So they will minimize all the columns. So I should choose my P with the P to commit to so as to maximize the amount I will be getting. Right? So this is what's called maximin, right? So this is the outcome of conservative reasoning. Suppose I'm disadvantaged by having to make the first move. I'm disadvantaged by having to commit to my mix strategy. Right? So this is what I'm going to get, maximin. And of course, the column player can reason in the same way, right? And we get a quantity called minimax. Okay, so that is two quantities, maximin and minimax. Right? And we denote them by V of R and V of C. Okay, let me illustrate by means of an example. Okay, so the formulas are ugly. They're especially ugly in PowerPoint. So let's do a 2x2 game when it all becomes easier to see. So let's say that this is the matrix. Again, numbers are what accrues to the row player. Right? So let's try to compute this quantity. Okay, so how do we compute that? Okay, I'm the row player, so I fix my P. I'm trying to figure out what the column player is going to do. So this is my P, satisfies P1 plus P2 is 1. So what's going to happen to me when I play P? Well, okay, is the column player can respond by choosing the first column. Right, then what I get would be 2P1 minus P2. Right, so this is what I'm going to get if they choose the first column. If they choose the second column, I'm going to get minus 3P1 plus 4P2. Right? And they have both of these options available to them. Right? They can choose the first column or the second column. They can also randomize. So they will choose the better option, the one that minimizes their loss. Right? So they're going to choose the column so that the amount I get is the minimum of those two. Okay. So now I know P2 is 1 minus P1. So I can rewrite it as a function of P1 only. Right, so this is just substituting P2 is 1 minus P1. Now, okay, let me graph it. So let me graph it as a function of P1. So 3P1 minus 1 looks like this. Kind of not quite, kind of the axes are drawn to different scales and not really to scale anyway. But kind of, this is the general shape. So the dark green thing looks like this. So I'm going to get the minimum. So for each value of P that I choose, I'm going to get the smaller of the two numbers. Right, so what I effectively get is this curve. Okay, so how should I choose my P1? Right, so the one that I should choose P1 that corresponds to the intersection point. Right, because this is where the fat green thing is maximized. Right, so I have to solve for 3P1 minus 1 equals 4 minus 7P1. Right, that solves out to P1 equals 1/2. Right, and that gives me a value of 1/2. So my VR, my maximum value in this case is 1/2. Okay, good. Right, so 1/2 is intuitive. What I can, if I mix 50/50, so then I can guarantee myself 1/2 no matter what that guy does. Right, so he can respond with this column, he can respond with that column. I guarantee myself 1/2. Okay, so let's do the same calculation for the other guy, right? So for the column player. So again, he fixes Q. Right, then he thinks, okay, so I fix Q, I mix between my columns. So the row player can react by playing the first column or the second column. First column, okay, so first column, what happens to me? So I lose 2Q1 minus 3Q2. Second row, I'm going to lose minus Q1 plus 4Q2. Right, so this is what I can lose. And the row player, being adversarial to me, will maximize my loss, because that they win. Right, so what I'm going to lose is the maximum of those two quantities. Okay, so again, let's graph that. So substitute kind of 1 minus Q1 for Q2 and graph. So I'm going to lose either this or that. Right, and of course I want to minimize my loss. So I'm reasoning in terms of loss, so therefore I'm still maximum. So, okay, so this is max. Okay, no, so I should have been drawing the other curve. Sorry, I should have been drawing the other curve. Right, so I'm minimizing, my goal is to minimize my loss. So, okay, so this orange squiggle is wrong. I should have had the other orange squiggle. I should flip the orange squiggle. Actually, let me see if I can quickly flip the orange squiggle. Kind of not to confuse you. Okay, so this is the right orange squiggle. Right? So max, right, so this is going to be my loss, and I'm trying to minimize my loss. Right, so I'm choosing, so it's minimized, the answer is still the same though. Right, so it's minimized where the 2 points intersect. Right, so it's minimized at 7/10. Okay, 7/10, whatever. So what is my actual loss in that case? So I substitute 7/10, let's say here. 35/10 minus 3, well, 0.5, 1/2. Right, so this is my loss. So I can guarantee myself a loss of at most 1/2. Okay, now remember previous slide. Very different numbers, kind of different calculation, different lines, different intersection point, but also 1/2. Right, so what one player can guarantee to themselves as the win is what the other player can guarantee themselves as a loss. Is this a coincidence? Turns out no. Turns out these two numbers, V of R and V of C, are always equal. And an easy way to see that is by LP duality. Right? So this is what we are going to do next. So again, so these are our friends, Maximin and Minimax. So let's look at Maximin. Okay. How can you, okay, so the question now is, how can you compute Maximin by linear program? Right, so, okay, your variables are P's. Right, so your input is aij's, your variables are p's. How can you set up a linear program that computes exactly this quantity? Tricky, right? Okay, so it's sort of the right shape. It's maximizing something, and there's linear something, but there's also a min, right? And min is not a linear function. Here is a trick for capturing expressions like that by linear program. So we introduce, okay, so let's assume that all entries of A are positive, makes my life easier. It's without loss of generality. I can explain that later if it's important. Okay, here's a trick. So let me introduce a new variable z, and this z will play the role of the minimum of these linear expressions. So how do you ensure that z is a minimum of these linear expressions? Well, I have to say that z is at most every single one of them. At most the first one, at most the second one, at most the last one. Right, and I'm maximizing it. If I'm maximizing something subject to these upper bounds, right? So then it's maximized exactly when it meets kind of the minimum of all these quantities. I cannot push past the minimum of these things, but if I'm pushing it up, there's no reason I should stop earlier. Right? So z that satisfies these constraints and is maximized is exactly the minimum of those things. Right? And I'm maximizing this quantity. So I'm maximizing over all possible choices of P and Z. Now if P are fixed, then the maximum value of Z is exactly the min, right? And I also have the freedom of choosing P, so I'm maximizing the whole things for all choices of P. Right, so this is my LP. Okay, I also need to have the constraint that my p's are probabilities and non-negative. So I don't have to say that the sum is equal to 1. I'd rather have inequality because I like my LPs in standard form, and I have to say they're all non-negative. So by the way, why can I say that it's at most? Why is it that I don't have to put an equality here? Yes, because all entries of my matrix are positive, right? So I'm better off. So if my goal is to maximize, I'm better off kind of using up the entire unit, right? So if the sum is strictly less than 1, I can make it slightly more, right? I can sort of take the tight constraint and jiggle it slightly and get more value. Okay, intuitively. Okay, so this is my LP. Okay, so that's not the easiest LP you've seen, but I hope it makes sense. Makes sense, mostly. Okay, so now the real fun begins. So let's take the dual of this LP. Okay, so it's written slightly non-standardly, but it's still a standard maximization LP. I'm maximizing a linear function subject to constraints, right? So these are constraints of the form at most 0. I just have to move everything in the left-hand side, right? So that all my variables are on the left, and then the constant on the right is just 0. Right, and then I have this one constraint with non-trivial right-hand side. Okay, so I have one constraint. So I have one constraint for each row, column. Okay, so I have n constraints. I have n constraints, so I need a variable. In the dual LP, I need a variable for each of these constraints. Right, so I need n new variables. Right, so I need, okay, so n is the number of columns, so I need variables q1 to qn. And I also need one variable for this constraint. Right, so we have a dual variable for each constraint. Okay, so now we have these variables, so think of them as kind of q1, qn, y. So now how do we, okay, what is the objective function going to look like? So remember, in the objective function, we multiply the right-hand side by the variable. And most of the right-hand sides are 0, and here is the one non-trivial right-hand side. Right, so in my objective function, I'll just have this one variable y, and I will be minimizing it. So my linear program will be minimizing y subject to some constraints. Okay, so what are these? So I'm minimizing y. So what are the constraints? So I get a constraint. So I get a constraint for each variable of the original LP. Right, so I get, okay, so I have z, so I have constraints for z. And I have constraints for each of pi. Right, and most of these constraints, the constraints that correspond to pi's, will be of the form at least 0, because pi occurs here with 0 coefficient. Right, and the constraint that corresponds to z will be at least 1, because z occurs with 1 coefficient here. Okay, so what are they going to look like? Well, okay. So let's first think about, okay, so let's think about the constraint that corresponds to P1. So P1 happens here with coefficient 1, that's y, right? So y multiplied by 1. Right, so here I moved everything to the left-hand side, so all the PI's occur here with minuses. Right, so P1 occurs here with coefficient minus A1n, here with coefficient minus A11. Right, and these are the coefficients by which I multiply the respective q's. Right, so this is the constraint I get for P1. Right, so each variable gives me one constraint, so this is the constraint I get for P1. Right, so y, the variable for this constraint comes with coefficient 1, and others come with coefficients minus A1j. Okay, and I do this for all of them. Okay, so, yeah, okay. So what do I get for z? So z occurs with 0 coefficient here and positively throughout. Right, so I get q1 plus etc. plus qn is at least 1. It's at least 1. Okay, so I flip. Okay, so I flip the sign, which is cheating. Right, so actually, okay, so it's at least 1. Okay, so it's at least 1, but in fact, okay, so it's Okay, so if I just take the dual, I get at least 1, right? And then I observe that it's in my best interest to set it exactly to 1, right? And therefore I can also write it as at most 1, right? So I don't. So maybe this is cheating too much, but certainly I can write it as equals to 1. Right, so it's at least 1, and I don't benefit from making it bigger than 1. Right, so therefore it's equal to 1. So let's say that this is equal to 1. Okay, so suppose that this is what it says. Suppose that this says sum of QIs equals to 1. Right, so all QIs are non-negative, Y is non-negative, and I have this. Okay, so how do I interpret that? Right, so this is saying that Y is at least this expression, and Y is at least that expression, and at least each one of those expressions, and I'm trying to minimize it. So what I'm minimizing now is the max of these expressions. So I'm minimizing the max of expressions of this form. Does this look familiar? Minimizing a max of these linear expressions. Right, so that's exactly the minimax value. Right, so if you look at the expression for VC, for the minimax value, that's exactly what computed by this dual LP. Right, so in other words, so if you start with VC and try to compute and try to write down the LP for it, the way we did here, you will arrive to basically this LP. Right, so there's kind of some fudging here with this equality. So I'll try to I'll try to make sure it's explained better in the lecture notes. But it's actually legit. So I sort of glossed over it in the slides, but it's legit. Right, so the dual LP then computes exactly V of C. Okay, so what we established is the examples we've seen in the previous slide, where VP was equal to V of C, was not an accident, it's always true. Minimax value is equal to the maximum value. Okay, what does it have to do with Nash equilibrium? We started with Nash equilibrium, and then we sort of got sidetracked into this minimax maximum. Well, let's get back to Nash equilibrium. Okay, so I sort of didn't say it explicitly, but I thought you understood. Because of strong duality, we now have that V of R equals V of C, right? Because these are primal and dual linear programs. One computes V of R, the other computes V of C. Therefore, by strong duality theorem, they're equal. Okay, so now let me take this P, vector P, that actually achieves the objective value for the first LP. Let me take P in argmax of min, so this thing. Okay, so it's a strategy. Right, and let me fix the strategy for the second player. Right, the maximum strategy and the minimax strategy. I'm going to argue that these actually form a Nash equilibrium in mixed strategies. Okay, why is that? It's sort of not that hard to see, but let me talk you through it. So suppose I'm the role player. Suppose I play P. So by playing P, I ensure to myself that I get VR no matter what my opponent plays. Right? So if I play P, kind of no matter, right? So I'm maximizing the worst thing that can happen to me. No matter which column my opponent chooses, or even if they're randomized, I still get V of R. Right? Okay, so in particular, I get V of R if my opponent plays Q. Right? I get it no matter what he does, so in particular, I get it if he plays Q. Okay, I'm guaranteed V of R. Now, okay, so let's look at this other guy. Right? This other guy, when he plays Q, he loses at most V of C, no matter what I play. Right? So he gets his minimax value. Right? So he's guaranteed himself V of C. Right? And this is V of R. So he loses at most that. Okay, I didn't say anything new so far. Okay, so here's a sort of mildly new idea. No mixed strategies can give me more than V of R against C. Right? So why is that? Because he's playing Q, so he is guaranteed to lose at most V of R. Right? V of C, which is V of R. He's guaranteed to lose at most that, no matter what I do. So even if I try now to deviate from my P, I cannot force him to lose more. Right? And therefore I cannot win more. Right? So therefore by deviating, I cannot get more than my V of R. Right? Because he has guaranteed to himself this payoff against any possible action of mine. Right? And therefore, what I'm currently playing is my best response. I'm getting V of R equal to V of C, and I cannot do better because my opponent has guaranteed to himself V of C. Right? Therefore, I'm playing the best response. And of course, symmetrically, he's playing his best response. Right, so this combination of kind of vectors, which we get by solving the linear program, are actually Nash equilibrium. Right, so we established two things. First, Nash equilibrium exists. First, we can actually efficiently compute it. We can efficiently compute it because it's a solution to a linear program. Right, and linear programs can be solved efficiently, both theoretically and practically. Okay, so that's an application of LP duality for you, so zero-sum games. So these same ideas have interesting applications also in the analysis of randomized algorithms. So you'll learn about that if you take probability and computing. I don't really have time to go into that. Right? But this sort of general minimax maximin idea is very powerful. Right? And it basically corresponds to LP duality. Okay, so that's that. Any questions about this? So this is the watershed moment. So we are done with the kind of polynomial time solvable problems in this course. So in this lecture, next lecture, and possibly also next week, in the rest of this lecture and then possibly next week, I'm going to talk about hard problems. Okay, so first we'll talk about what it means for a problem to be hard, and you've seen a bit of that in models of computation, so I'm going to build on that. Right, and then briefly we'll talk about how to deal with hard problems. So let me start today. I realize it's a vision for most of you, but it's a vision from a slightly different angle compared to models of computation. Right, and maybe if some of you took models of computation last year, I'm not sure if any such people are in the room, then you haven't really seen it properly. Okay, so hard versus easy problems. Okay, so far we discussed problems that admit efficient solutions. Right, so minimum spanning tree, shortest path, network flows. For all of those, we designed algorithms whose running time was like at most quadratic, well, cubic in the input size. Okay, so how do we define efficient? Well, the common traditional answer, efficient is, well, admits an algorithm whose running time scales polynomially with the size of the input. Okay, so why? You can reasonably ask why. Well, for instance, if you have two algorithms and one is n to the power 100, why is it better than 2 to the power n? Because on most practical instances it's not. Right? Or at least on many reasonable size instances it's not. Well, so there are a bunch of answers, so which should be familiar for models of computation. Well, polynomial time there's model independence. So we can talk about polynomial time as a well-defined notion. Polynomial time on deterministic Turing machine pretty much means polynomial time in any reasonable model of computation. Right, and you cannot say the thing for other more restrictive notions of efficient. Right? And so it's closed under composition. Right, so if I have a program that seems to run in polynomial time but includes goes to subroutines, but these subroutines also run in polynomial time, then I know my program is polynomial time. Right, so this is useful. Being closed under composition is extremely useful. In fact, I'm going to see it today. Right, and in practice, of course, we don't get into the hundreds. So I think the worst I've ever seen for a real algorithm would be like n to the power 6, 7, and in practice that tends to be quickly improved to lower degrees. Right, so usually when you manage to design a polynomial time algorithm for a problem, it's typically not n to the 100. So it seems like a reasonable notion of efficient. So again, you must have seen that in models computation. Okay. So polynomial is good, not polynomial is bad. So can we prove that something is not polynomial time solvable? Well, sort of. So there's a bunch of artificial problems for which we can solve that. But for interesting problems, for ones that we really want to prove that, ones that we haven't been able to solve in polynomial time, we as a society, we typically don't know how to prove that. Okay, so what can you do? Right, so computer science, since its inception, struggled with that issue. Right, if we cannot do something, we want to prove that it's impossible. Right, and this impossibility results seem to be awfully difficult to come by. Right, so here's an alternative approach that computer scientists came up with. We'll define a class of problems which includes interesting problems not known to be solvable in polynomial time. Right, so we want to have a sort of formal class of hard problems. And then we're going to show that all problems in this class are in fact equally hard. So if one can be solved in polynomial time, then another problem can also be solved in polynomial time. So they sort of all have the same complexity. Right? And then if you're facing a specific problem that you're trying to solve and you fail to design a polynomial time algorithm, all we have to prove that it actually belongs to that class, right? That it's one of those equally hard problems, right? So you have to show that your problem is as hard as problems in this class. So that's my favorite illustration, right? So that's Gary Johnson. So I'm not sure if you can read this. It says, I can't find an efficient algorithm, but neither can all these famous people, right? So the problem you are trying to solve, right, is as hard as lots of problems kind of people have been struggling with for years, right? So presumably it's not solvable, right? So it's like saying, okay, so if I solved that specific task you asked me to do, I wouldn't just solve that, I would win a Nobel Prize, Turing Prize, whatever, right? I'd be rich and famous. Okay, so how can we accomplish this agenda? Well, for that we need the notion of reductions. Again, something that should be familiar for models of computation. Okay, so we'll talk about reductions between decision problems, problems that admit yes-no answer. Okay, so examples would be, does a given bipartite graph admit a perfect matching? Or is a given Boolean formula satisfiable? Or maybe, is there flow of size at least d? Right? So sometimes it's more useful to talk about optimization problem, like find the maximum flow. But when we talk about reductions and complexity, it's useful to talk about decision problems. Okay, and we'll distinguish answer, which is yes or no, from a solution. So a solution would be like a matching or an assignment or a flow, like an actual kind of way to accomplishing that answer. Right? So it's useful to think of those as two separate things. Okay, so here's a definition. Again, should be familiar for models of computation. We say that the decision problem A is polynomial time reducible to decision problem B if the natural thing holds. If there's a polynomial time computable mapping that takes instances of A to instances of B so that yes instances are mapped to yes instances and no instances are mapped to no instances. Right? So no to no is captured by this if thing. Right? Okay, so that effective, okay, in practice this is what it means to reduce a problem. Right? So you take your problem, you transform it efficiently into a different problem so that answers are preserved. Yes is yes and no is no. Right? So in fact we've seen examples of reductions. Right? So one reduction we've seen is reducing bipartite matching to max flow. Right? So that was a polynomial time reduction. Okay. So that should be intuitive enough. Okay, so what the key property of inductions? Suppose I have reduced the problem to an easy problem, right? Then my problem is easy, right? Okay, so obvious, right? So if I have a problem and I manage to quickly and easily reduce it to something easy, I can thereby solve my problem. So let's prove it formally, because easy means something formal in this case. Easy means polytime. Okay, so let's look at the reduction. So my algorithm is what you expect it to be. So I take an instance of A, compute the reduction, run kind of my algorithm for the new problem on the reduced instance, and return the answer. Okay, so it's correct because yes instances map to yes instances, no instances map to no instances. Running time is slightly more subtle. Okay, so first, computing the reduction is efficient, right? It's polynomial time. Second, and this is slightly more subtle point, when I run B, I run it on when I run my algorithm for B, I run it on an instance of size of M of A. Right? So the size of that instance is at most polynomial in the size of my original instance. Why? Because I computed it in polynomial time. In polynomial time, I couldn't produce something very long. I could produce something of at most polynomial length. Right? So I now run my algorithm for B on an input whose size is polynomial in the size of the original input. Right? And now I use the fact that polynomials compose. So I run the polynomial time algorithm on polynomial size input. Right? So my overall running time is a composition of these two polynomials, which is still a polynomial. Right? So more concretely, if I took an instance of size n, took instance of A of size n, my reduction transformed it in an instance of size n squared of B, and my algorithm for B is cubic, my overall running time now to solve this instance of B would be n squared to the third power, so n to the 6, right? So slower than just solving B, but still polynomial, because polynomials compose. Okay, so that's reductions. Okay, so we are getting to kind of our definition of the class of interesting problems. right? And that's kind of non-determinism. Okay, so P is our class of easy problems. So these are decision problems that can be solved by a deterministic Turing machine. NP is the class of decision problems that can be solved in polynomial time by a non-deterministic Turing machine. Okay, so you all remember non-deterministic Turing machines. Hopefully remember the definition of NP. So I hope Tom Mellon was more successful explaining it than I was last year, because in my algorithms exam last year I asked to find the class NP, and I got answers I want to unsee. Right, so this is NP. Like, seriously, it is one thing we all want you to know after you graduate. We want you to know that NP is what is efficiently solvable in a non-deterministic Turing machine. One answer, I definitely don't want to hear something that is not polynomial time solvable. And believe it or not, some Oxford students actually gave that answer in the exam. Oh well, right, okay, hopefully this is not going to happen this year, right, I warned you. Okay, so P and NP. Okay, so we know it's easy to see that P is in NP because non-determinism is more powerful than determinism. Right? So equivalent definition of NP is problems for which a candidate solution can be verified in polynomial time. Right? Okay, so why is that? Well, if you can solve something non-deterministically, if you can branch non-deterministically and look for a solution, that's sort of like guessing that solution and then verifying that it works. Again, something that should be familiar for models of computation. Okay, so let's look at examples of problems in NP. Problems that are solved by non-deterministic Turing machines. So, okay, so here's one example. Is there a flow of size x in a given network? So why is it in NP? Well, two answers here. First, because we can actually, given a network, we can actually solve it and find the maximum flow and can compare its value to x. Right? Because because this problem is actually in P, but the other answer is in NP because we can guess the amount of flow on each edge and then easily check that it's valid flow and its size is at least x. Right? So this is a problem that is easy to verify. So in other words, a non-deterministic Turing machine could branch by guessing what is the flow on each edge. Okay, so I'm sort of fudging over details here, assuming it's all integer. Right? And then verify that it's a valid flow. Okay, so maybe an easy example is a given integer x composite. So we don't know how to solve it in polynomial time, but we know how to verify a solution. Right, so it can be solved by a non-deterministic Turing machine by branching over all possible numbers between 1 and x. Right, and for each such number, dividing x by that number and checking if the result is integer. Right, or equivalently, kind of given a potential solution, two integers, y, z, we can easily verify if this is actually a valid solution. Right? So for all these problems, a potential solution is easy to verify. So again, does a given Boolean formula have a satisfying assignment? Right? So given an assignment, you can easily verify that it's actually valid. So another problem, okay, and this one, okay, so I want you to pay attention now because this problem will be important kind of for the rest of the course. This is going to be our kind of paradigmatic NP-hard problem. This is vertex cover. So vertex cover is asking for a set of vertices of size at most k that covers every edge. So is there a set of vertices of size at most k such that for every edge, at least one of its endpoints is in the set? Right? So we want to cover edges by vertices, we want every edge to be covered. Right? So this is vertex cover. We ask if there is a cover of size at most k. Okay, so how do we verify if with a given solution is a valid vertex cover? Well, we check that it's a set of vertices, we check that it has size at most k, and we check that it actually covers all edges. All of that is easy to check. Okay, so these are all problems in NP. Right, so one of my examples is a really easy problem, polytime solvable. Right, so others are just problems where it's easy to verify a solution, but maybe not obvious how you can find one. Okay, and now NP-hard problems are problems that are as hard as anything in NP. So remember we had this agenda of establishing a class of problems that contain interesting problems and are known to be mutually equivalent. Right, so I'm getting there with the definition of NP hardness. A problem is said to be NP hard if all problems in NP can be reduced to it in polynomial time. Right, so these are hardest problems in NP. And we say that problems are NP complete if they're NP hard and also in NP. So a problem can be harder than everything in NP, because it's genuinely very, very hard. It's even harder than NP. You can reduce everything in NP to it, but you don't know how to, but it's not necessarily in NP because maybe you don't know how to verify a solution to it. Right? So a problem can be undecidable and still NP hard. So NP hard is something that is hard but not too hard. And NP complete is something that is hard but not too hard. NP hard but still in NP. Okay, and NP complete is our class of interesting pairwise equivalent problems. So there's a theorem, again proved in models of computation, that SAT is one of those problems. SAT is NP complete. Right? All problems in NP can be reduced to it and it's in NP. So we have argued that it's in NP, right? And then, so there was a proof, that was again sketched out in the models of computation, that reduced any problem in NP to SAT by encoding the computation of non-deterministic Turing machine as a polysize table, right? And then encoding this table as a Boolean formula in DNF, right? And then satisfying assignment corresponded to accepting computation, right? So there are more details about that you can find in subset, right? But SAT is NP complete. Okay. So now the million-dollar question is, we have the complexity class NP, we have the complexity class P, we have NP hard problems that include some problems in NP and some problem outside of NP. We have the intersection that is NP complete. And the really interesting question is whether this picture is correct. That is, whether this intersection actually exists. Right? So the million-dollar question is whether P equals to NP. Why is it captured by this question? Well, because if any NP complete problem is actually in P, then, well, if it's NP complete, it means that all problems in NP are reduced to it. Right? So if it actually is in P, this means that all problems in NP can actually be reduced to a polynomial size problem. Polynomial times solvable problem. Right? And thereby they can also be efficiently solved. Right? So if there's even one point in this intersection, if there's even one problem that is both NP complete and in P, then the class NP collapses to P. Then everything in NP can actually be solved in polynomial time. And it's literally a million-dollar question because there's a prize out there that offers $1 million to those who solve it. Okay, so we are not going to make much progress about solving it, but at least we are going to learn about interesting specimen in the class NP. So what you learned in models of computation is that SAT, satisfiability, is actually a problem that is NP complete. So what we're going to see tomorrow, and I think also next week, are further examples of NP complete problems that don't involve boring logical formulas. Okay, some of you may like logical formulas, I don't really, but but involve instead nice graph theoretic objects, like vertex cover, independent set, dominating set, right? So various nice combinatorial and graph theoretic concepts. Right, so this will be the combinatorial side of NP hardness, seeing nice combinatorial problems that are NP hard, and seeing why they're NP hard. Right, so that's the plan for tomorrow and beginning of next week. That's it. Okay, so whatever slides I didn't cover, I'll move them to the next lecture. I'll move them to tomorrow.
Yes. Yes, for
Cheers.